Alright, it's a Slinky, and it says every wave, regardless of how high and forceful it crests, must eventually collapse within itself. So this is going to introduce us to the ideas and vocabulary that are associated with waves, which is what we're going to be studying for the next month or so. So let's go ahead and take a look at our learning goals. And the first one is that you be able to differentiate between a transverse wave and a longitudinal wave. Those are the two main different types of waves. There are a couple of other ones that we're not going to cover, but you need to be able to give examples of these, show what the difference is, talk about the various vocabulary terms in terms of these waves. So it's really important that you be able to differentiate between those. You also need to be able to identify the vocabulary terms associated with different types of waves and be able to say what effect they have on the waves. And you need to be able to predict the result of interference between two waves. So the first thing we want to do is we want to look at something called simple harmonic motion. Simple harmonic motion is anything that you have that's somewhat repetitive in nature. And so if you were to take a look at this, you'd say, okay, force is proportional to displacement. Really what that's saying is that as you get further away from this equilibrium point, the force that wants to bring it back increases. So whenever you have a pendulum, when the pendulum is right here, there's just a very small force trying to bring it back to the middle. But as you get further and further away, the force gets larger and larger and larger. Simple harmonic motion is also something that repeats itself with regularity. And examples of those are mass and spring. So whenever you have a mass on a spring, it oscillates up and down. It's repetitive and it's restoring forces proportional to how far it is away. And then also, really what we're looking at now is waves. Okay, waves are examples of simple harmonic motion in the fact that they're repetitive and that the force trying to restore it to that middle point is always proportional to how far it goes away. So, let's look at waves. Waves are traveling energy. Now, a lot of people get confused here because they say, okay, well, you've got this ocean wave right here, and clearly the water is moving up and down. That is true. Whenever you have an ocean wave, the water is moving, but the wave itself is traveling within the water. Okay, so whenever the wave travels within the water, it makes the water move up and down, but the water itself is not the wave. The wave is just energy that travels through matter. So waves disturb matter, but they are not made of matter. So it's a really important distinction that you need to know, and that comes into play later when we talk about interference, because if waves were matter, you can't have matter and matter occupy the same space at the same time, but you can with energy. So let's go ahead and look a little bit more into detail about waves. You say waves are emitted in all directions equally. So you can kind of see that in this picture right here. Whenever you have a drop hit the water, it emanates in a circle as it goes outward. Okay, but realistically, most waves that we're going to talk about, like light and sound, emanate in three dimensions. So it's going to go up, down, left, right, and then also, towards you and away from you. So you need to be able to think about them in three dimensions. Waves will continue forever unless dampened. Now, a dampened wave is one in which it starts off kind of big and then it gets smaller and smaller and smaller and smaller. Now, that tends to happen a lot of times with things like sound. Not so much with light, but with sound, where the sound gets softer and softer and softer as you get further away. And those waves travel at constant velocity. Okay, depending on what media they travel in, they're gonna maintain that velocity. We won't really talk about the acceleration of waves or the deceleration of waves and those sorts of things. So, the first type of wave is called a transverse wave. And a transverse wave is one in which the oscillation is perpendicular to the direction of motion. So this is one of these things that I really think you should take a look at. There's an animation by Dr. Dan Russell. If you kind of just type that into your search bar, you can actually see what this thing looks like when it's moving. But realistically, what it looks like is the wave is traveling from left to right. And you clearly see this bump would travel from left to right. It would move this way. But if you were to look at an individual dot, when you look at an individual dot, it just moves up and down. The individual dot doesn't move left or right, but the wave travels from left to right, and the individual matter moves up and down. So what we're saying here is that the oscillation of the matter, so what the matter does is the matter goes up and down as the wave moves left and right. So those two things are perpendicular to one another. Since they're perpendicular to one another, you have what we call a transverse wave. Examples of transverse waves are light. Light is a great example of a transverse wave. It oscillates up and down as it moves this way. Also oscillates left and right, but we'll get to that a little bit later. And also a wave on a string. So if you did the Slinky lab, whenever you move the Slinky up, it generates kind of a pulse wave that moves this way, but the oscillation is this way. So those are examples of transverse waves. There's some key vocabulary that's associated with the transverse wave. Some of the key vocabulary associated with waves is period, first off. Period is the time that it takes to reach identical points on a wave. So if you were to start at the wave right here, the identical point on the wave would be here, okay, not here. Okay, a lot of people say, well, it's at the same place on the graph, and that's true, but if you were to look at it, the wave is actually moving down right here, it's moving up right here, and it's moving down right here. So these are the two identical places on the wave, not that one. So period is the time it takes to get between two identical points on a wave. It's measured in seconds, okay? And you can tell it from on a graph that is a time versus amplitude graph. And you have to be careful when you're looking at waves, because a lot of times this is time, but there are other occasions in which it's going to be something like distance, where you can measure wavelengths. So you got to be real careful when you look at the x-axis when you're talking about waves. The second thing is frequency. Frequency is the inverse of period. Okay, where period is the time that it takes to complete a cycle. Okay, to complete one cycle of the wave. Frequency is the number of cycles that pass in 1 second. So those things are actually inverses of one another. We'll look at the mathematical relationship a little bit later, but basically as the period goes up, the frequency goes down. Now, waves are easily expressed as a sine or a cosine graph, and that's kind of what you see right here. You can see this graph right here. This is a sine or cosine graph. It just kind of depends on the parts of the function, but you see how it goes up and it comes down. This right here is a sine or cosine graph in your calculator. Okay. A couple other key points right here is you have a crest, and a crest is the highest point of a wave. It represents the point of maximum energy. Okay, maximum energy. The trough is the lowest point on the wave, and it represents the point of minimum energy. And then this right here, this line right in between, okay, it should be halfway through, is called the equilibrium line. And it's halfway between the crest and the trough. And that's kind of like the middle point that you kind of measure everything from. Wavelength is the distance between identical parts of subsequent waves. So remember when we had period right here, okay, here we have wavelength, and it's the same thing, distance to distance, identical parts of the wave, but the difference is that this is a distance versus amplitude graph. Okay, so you have to be real careful and check the axis to see what you can get there. But whenever you have the distance, that allows you to calculate or to figure out what the wavelength is. Media is also really important when we talk about waves, and the media is what the wave travels in. So if it's a water wave, the wave is traveling in water. If it's light, it could be traveling in air, a vacuum. If it's sound, it could be traveling in water or steel. It really matters what the media is, because that's going to affect the wave properties. Wave energy. As the amplitude increases, energy increases. So whenever you increase the energy of a wave, okay, it's going to increase in amplitude. It's not going to change anything else. It's just going to increase in amplitude. So amplitude is directly related to the energy that's there. So we measure amplitude as the distance from this equilibrium line to the crest or the trough. It should be the same. So like, for example, on this green wave right here, it could be something like 1, and on this wave right here, it could be something like 5. Okay, that would be the amplitude, and since it has a higher amplitude, we would say it has more energy. Really, the third type of wave is called a pulse wave. And a pulse wave is a type of transverse wave that's formed by a quick oscillation of the rope. So we don't really say that it's a different type of wave. It's just like a single transverse wave. And you saw this when you did the Slinky lab, is you would send a single pulse down this string. And when you sent that single pulse down the string, there was no other trough or another crest or anything like that. It was just one single wave that looks like that. And that's what we call a pulse wave. A lot of times pulse waves are really useful for when we're trying to look at things like reflection. Okay, so we come to example A1. Example A1 says, a pendulum swings such that it travels 35 centimeters from the equilibrium point. Sketch a graph of displacement versus time and label the following. Okay, so we want to look at this, and we know we want to look at displacement versus time. So we would say, okay, displacement and time, and we would go ahead and draw the graph. So it's going to cycle back and forth like a sine or a cosine graph, and it's going to look like that. We want to look at our points of interest right here. We would say that the point of maximum energy is the crest. The point of minimum energy is the trough. Okay, this distance between the equilibrium line and the crest is the amplitude. Okay, we've already labeled this as the equilibrium line. And the period would be points between subsequent waves. So you can say crest to crest, that would be a period, or you could say trough to trough, and that would be a period, or you can even pick a point in the middle and say from this first point to the same point when you've completed one wave. So it's really important that you be able to identify the key vocabulary terms on a graph and construct your own graphs. Now, people say, but what about this 35 centimeters right here? Okay, that 35 centimeters would have become really important if we were labeling the graph. It should be at 35 centimeters. And this trough should be at negative 35 centimeters. Okay, because that's how far it goes from one side to the other. And you should know that a pendulum that swings 35 centimeters this way will swing 35 centimeters that way. Okay, so next we come to example A2. It says, what direction do particles oscillate? This right here is a transverse wave, and it clearly shows that the wave is moving from left to right. So since it's moving from left to right, there are two possible answers. Okay, the first one, anything that is perpendicular to that left to right motion, and that would be up and down. Okay, so this right here is one obvious answer, but there is a second answer as well. If you think about it three-dimensionally, in addition to up and down being perpendicular to left and right, you also have this kind of into the page and out of the page right here, kind of that z-axis. That right there would also be a possible answer. The next type of wave we're going to talk about is a longitudinal wave, and a longitudinal one is one that oscillates in the same direction of motion. And once again, this is something that I think you should take a look at this animation. If you Google Dr. Dan Russell Graduate Program Acoustic Penn State, you'll come up across this simulation right here of a longitudinal wave. And what this says is, as the wave moves from left to right, okay, what you'll see is that the waves, or the oscillation of the particles, also move left to right. So you'll see a left to right motion and a left to right motion, and as a result of that, what you see is you see these kind of clusters of waves right here. Okay, so you'll see where there's a bunch of these particles together, and then they're kind of spread out, and then a bunch of these particles together, and then it's spread out, and then a bunch of these particles together, and that right there is kind of the hallmark of a longitudinal wave. Now, longitudinal waves are a little bit different than transverse waves because you're not going to see a lot of the same vocabulary. Instead, you'll see things like this. Waves that oscillate in the same direction of motion, okay, sometimes it's called a compression wave, sometimes it's called a longitudinal wave. Now, the reason why sometimes it's called a compression wave is because the compression is the same thing as a crest. That point where it's kind of squeezed together right there, that right there represents a compression, or a point of maximum energy. So when I say they're equal to each other, what I'm saying is it's the same thing on two different waves. It's the maximum energy in each point. Now, other than the compression, you have this region where it's stretched out. That right there represents a rarefaction. A rarefaction is the same thing as a trough. Okay, it's the point of minimum energy, kind of like a trough that you saw on a transverse wave. Now, examples of compression or longitudinal waves tend to be things like sounds. Sounds are examples of molecules being squeezed together and then separated, and squeezed together and separated. So, whereas light is an excellent example of a transverse wave, sound is an excellent example of a compression wave. So on this one it says, earthquakes contain both transverse and longitudinal waves. Only one of these waves is destructive. Speculate on which and justify your answer using the clear method. So remember, if you have an earthquake, most of the damage is done whenever the earth kind of moves up and down and breaks up buildings and roads and things like that. You see that here, where because the road went up and down, it kind of cracked the street open. So the one that moves up and down would be an example of a transverse wave. Okay, it's a transverse wave. And the evidence that you have is destruction is caused by up and down motion. Okay, and the reasoning that we have is transverse waves oscillate perpendicular to the direction of motion. So as the earthquake wave travels through the ground, it's the transverse part of it that's going to make the earth go up and down. In this one it says, which of the following is analogous to the crest of a transverse wave? And so if you were to look at this, remember a crest is the same thing as a compression. So this is our correct answer. Okay, it's the compression, or A. B would be the example of a trough. C is not really anything. And if you were to look at D, D actually represents about 2.5 wavelengths. Because remember, um, on a transverse wave, a crest and a trough together could make one wavelength. So if you have a compression and a trough, and then another compression, that actually represents about 2.5 wavelengths. All right, so because since waves are actually made out of energy and not matter, you can actually have two waves occupy the same space at the same time. And that's what makes waves unique when compared to the things that we've covered before. Because before, if you had a wooden block and a wooden block, there's no way for you to take those two wooden blocks and have them occupy the same space at the same time. It wouldn't happen. You can't physically move them together. Waves are different because they're energy, they can do this. And you see this pattern right here. This is actually called an interference pattern. Okay, it's an interference pattern. And what you see is you see waves generated at one source and waves generated at another source. And instead of seeing the circular pattern that we would expect with waves, you see this odd pattern in between. And that odd pattern in between is a result of, once again, interference. So there's some rules that we need to look at whenever we talk about interference that are actually pretty straightforward. The first one says the waves affect each other to cause a new wave or a superposition. So what you have is you have a single wave right here, and you have a single wave right here. And actually off a little bit in the picture because of exporting it to PowerPoint. But if you were to have these two things line up right here, these two things right here would create a larger wave. Okay, it's a constructive interference. Okay, whenever you have two waves together, what you do is you basically add the waves together. So let me go ahead and draw this out so you can see it a little bit better. But if you have the first wave right here, and you have the second wave right here, those two things add up together. And so what you do is you were to take the amplitude of each of these, like say the amplitude was 1 and 2, you would take the amplitude of those things and you would add them together, and the new resulting wave would be the combination of those two. So 1 plus 2 is 3. People say, well, what about what over here? Well, here you would have -1 and -2. Well, that would result in -3. So the superposition is the adding together of the two individual waves. Now, whenever you have two waves that add together in a constructive manner, and by constructive I mean it has a larger amplitude. So 1 plus 2 is 3. -1 plus -2 is -3. Both of those are examples of larger amplitudes. So because of that, we would call this particular example constructive interference. But if you were to run into a case where you had a wave that looked like this and a wave that looked like this, whenever you were to add those two things together, let's say they have the same amplitude, 1 and -1, if you were to add those two waves together, you would actually end up with 0. Well, 0 is a smaller amplitude, so this would be called destructive interference. So basically, if the waves get bigger, it's constructive. If the waves get smaller, it's destructive. So, example C1 says a student is investigating the possibility of generating true noise cancellation headphones. Explain what would be necessary to truly cancel out a sound. So a sound is a wave, which I'm going to draw as just kind of a transverse wave, even though I know it's a compression wave. So if I have a wave that comes into my ear over here, okay, there's my ear, the only way to truly cancel out that sound is to produce a second wave that is the exact opposite. So whereas this wave comes in like this, I would need to produce a second wave that is the exact opposite of what I should be hearing, and as a result, those two things will cancel each other out. Okay, that would be extremely difficult to do because you'd have to have a speaker kind of detect what sound is there and then broadcast a secondary opposite sound in order to cancel it out. Okay, so true noise cancellation headphones aren't really the case. Now, what you can do is you can isolate yourself from the sound by having heavy padding and insulating and dampening the sound. Okay, really what these things do is they take the sound wave that is this and they make it dampen to the point where you can't really detect it. They're not really canceling it out. What they're doing is they're just dampening them more than anything. And our last example says when these two waves meet at point P, what will the resultant amplitude be? And people usually have issues with this at this point. They say there's no numbers. And if you look at it, you say, okay, well, when they get to point P, This thing right here is going to have an amplitude of A, and this thing right here is going to have an amplitude of negative A. Remember, whenever you do superposition, what you do is you add the two things together. So when I add A plus negative A, the resulting amplitude is 0. Okay, so that's the answer to my question. It says the resulting amplitude would be 0, and this is an example of destructive interference.